Hello, everyone, and welcome to this week's HoloTube with David Lowe, who is joining us from Brown University and will tell us about quantum chaos and unitary black hole evaporation. David, please take it away. Welcome. We're happy to have you.
Oh, well, thanks a lot. It's great to be part of the HoloTube finally. And yeah, I hope to sit in on a lot more meetings in the future. So yeah, I'll be talking about some work I did in collaboration with Lars Thorlacius from the University of Iceland, which I guess appeared back in March. I've been working on in some form for a while. We're going to be using ADS-CFT combined with some ideas from quantum chaos theory to get a better picture of black holes that actually evaporate down to nothing. So we won't actually use too many detailed features of ADS-CFT, and we'll expect most of these arguments will generalize to any kind of holographic model where, for me, holography means we have some kind of quantum mechanical description on some fixed geometric background with a continuous time. And I'll be working at large n, but finite n. I'm not really going to focus too much on taking a formal large n limit, because one really needs to keep terms that involve factors like e to the minus n in play in order to really see the effects of unitarity and how the evaporation process incorporates those effects. So one of the stumbling blocks that has held up development in this area is to just try and specify how you describe small black holes from the conformal field theory viewpoint. So we know very well how to do the big black holes where we can just turn on a finite temperature. You can't really do that with small black holes. So you need to find a way around that. So we'll be kind of using some ideas that I thought were nicely explicated by Mukhanov back, I guess, in the early 90s, but had been explored in other forms long before that. Just thinking about the evaporation process and essentially time reversing it. So that gives you some, like a cloud of outgoing radiation that you can describe well using conventional ADS-CFT techniques. For example, this HKLL map that I was involved in 15 years ago, where you can essentially build a group theoretic change of basis to go from operators in the conformal field theory to local bulk operators. So once we've kind of defined this Hilbert subspace in the conformal field theory that for the most part corresponds to these small black holes, we'll apply this eigenstate thermalization hypothesis to this Hilbert subspace. So I'm not going to prove that the CFT behaves chaotically or anything like that. There's been a lot of separate work in that direction. And of course, it's not true that the entire Hilbert subspace behaves chaotically. You have all these large n, you have a whole sector that you think is described by a large n integrable theory, for example, in the case of ADS5 and n equals 4 super Yang-Mills theory. So those are examples where you have no sign of chaos, But by the same token, you don't believe you're building black holes in any of those scattering processes that are integrable. So that there is a kind of separate Hilbert subspace there that is involved with these small black holes, and then there are signs of it that you can see, for example, in these 2D CFT computations where you can see some signs of quantum chaos emerging. Anyhow, so there's some Hilbert subspace of the CFT, and as with most approaches to quantum chaos, we will just use the kind of bare bones assumptions and apply this notion of eigenstate thermalization, which will give us a characterization of the matrix elements that will be needed to proceed with our calculations. So once we've assembled these facts, we can get estimates of corrections to semiclassical physics, and moreover see how semiclassical physics emerges from this Hilbert subspace. And we'll see there are special states that kind of behave like firewalls, but they're extremely rare. We'll be able to provide a more precise definition of how to build a typical state that behaves in a quasi-classical way. And for such states, we can give a prescription for computing infilling observables that actually will take us across the horizon. So if I have time, I will get to that. Actually, what time should I end?
Usually there are some questions along the way, and we end around 4, or you have 60 minutes roughly.
Okay.
But don't feel rushed.
Okay. Very good. Okay, so let me just begin by talking about this issue of small black holes. So as I mentioned, this was developed by Mukhanov. So he gave this kind of slightly fishy argument for computing the entropy of black holes just by thinking about a kind of cloud of Hawking radiation collapsing down and just counting the number of states in it. And it turns out Zurek had already done this about 20 years before. And you do kind of get the entropy right up to a factor of 4/3. So you get a little bit more entropy this way. But the trick of the idea was to not consider just a kind of general gas at fixed temperature, but to consider really a gas in a shell where all the particles are kind of radially directed toward the horizon of the black hole. So they've all got to kind of hit this horizon that has some finite solid angle associated with it. So when you take into account that kind of reduction, that thinning of the number of states, you get the black hole entropy correct up to just a numerical factor. So you can get the area law. You have some extra states here. And as we'll see in the following, there are extra states where these particles will just kind of scatter through each other. And if you like, that's kind of the part of the Hilbert space that is not behaving chaotically. You'll get some states that just scatter through and go back out to infinity without sitting inside the horizon for a long period of time. So, and again, I'm going to be talking about 3D CFT, so actually 4-dimensional black holes. And again, I'm going to be focusing on small black holes whose radius, whose horizon radius is much smaller than the radius of curvature of ADS. In fact, I'll make sure the lifetime m cubed, is also smaller than the radius of curvature of ADS. So they will get a good chance to evaporate before the negative cosmological constant starts to play an important role. Okay, so that's the kind of picture. As the black hole evaporates, the radiation becomes hotter. That's kind of shown by the colors in the diagram. And conversely, that means it can be kind of difficult to form a black hole in 4D. You really need either some Planck scale particles to get things started, or something akin to a supernova, where you get a lot of lower energy particles, but concentrated very close together. That is not the highest entropy situation, though. So it's really the time reverse of the typical evaporation process. It's more characteristic of the kind of highest entropy configurations. So that's the kind of picture we have. So we can essentially wait for this cloud of radiation to expand out to a radius of order, say, m cubed. So the black hole is now completely gone. And then the idea is going to be to try to apply conventional perturbative ADS-CFT methods to rebuild this cloud of gas and time reverse. So that's our strategy for building these initial and final states of black holes in the conformal field theory. So yeah, in a little more detail, we let the radiation expand out to some size d of order the lifetime of the black hole, which in 4D is of order m cubed. And we're going to make this radius of curvature of ADS much bigger than that. And once we've done that, we can use HKL to build kind of one by one these wave packets of light excitations, and then just combine them together. And because we've let things expand out so far, the 1/n effects will mean that the interactions between these individual elements will still be under control. So at leading order, we can just use vanilla HKLL to build these initial and final states by combining things. And yeah, as I was indicating, a key step here is to restrict the solid angle of the particles as they move in. So we're trying to hit an area of order m squared, the area of the horizon, and the sphere size is of order d. So the restriction on solid angle, it will thin our states by that kind of large factor. And then when you actually count the number of states, just doing a straightforward statistical entropy of that gas, you get that the entropy goes like m squared, the horizon area. And Zurek kind of did this in a very precise way in his 1983 paper, taking into account all the gray body factors and all that kind of thing. If you just model the black hole as a black body, you can actually calculate the factor analytically, and you get a 4/3, which also appears in Lukanov's paper by a much briefer and more intuitive argument. If you really take into account all the gray body factors, then that 4/3 turns into something that's a little bit closer to 1, but it's still bigger than 1. Okay, so yeah, if you focus on, say, the short wavelength particles, and kind of model them using geometric optics. You are essentially modeling them as you would a black body, and they contribute then a 4/3, but the longer wavelength particles will give you a slightly smaller factor. Okay, so you know, we're not 100% just building black holes with this set of conditions, but we're a little bit over complete, and that's something we can live with as long as we're not under complete and having to worry about remnants or something like that. We're reasonably happy at this point. So, okay, so we've got this Hilbert subspace, and I think I may have do some between my slides. Oh well. Yeah, let me just sketch this HKLL construction since one of my slides seems to have disappeared. So yeah, the idea is if we think of ADS as a kind of tin can, and we want to build say a local operator in the bulk, then we can get it by smearing in the CFT on space-like separated points from that point in the bulk that we're trying to build a local excitation at. What we really want to do in this calculation is then to further shift the time integrals down, and you know, we can essentially do that just by replacing these CFT operators up here by some, you know, series where we're, you know, just shifting it back to some reference time, and also including insertions of time derivatives of that operator. So in essence, we can shrink that integral, that smearing integral in the time direction to some narrow band, so that these are indeed some kind of creating some well-defined states in the conformal field theory, and the initial and final states can then be well separated on the boundary, even though they're actually fairly close together within an ADS radius of curvature in the bulk. Okay, so let's continue. Okay, so let's work with that idea then, and see how far we can push it. So to do that, we'll think about some of these ideas of quantum chaos. Let me just review a few facts about quantum chaos. So you know, we're just imagining we're doing quantum mechanics now. We have some Hamiltonian, and as you know, any Hamiltonian can be diagonalized. Energy eigenstates remain energy eigenstates, so that there's always this issue that in some sense there's no chaos in quantum mechanics. But the issue is more how you recover the classical limit or the semiclassical limit. And what tends to be true in these theories that exhibit quantum chaos is that these energy eigenstates are highly delocalized. So it can happen that when you start building wave packets that are localized, you're having to sum over many different energy eigenstates in order to get such wave packets. And then chaos can emerge as you take a kind of semi-classical limit. So once you start having these localized wave packets interact, chaotic behavior can naturally arise. And one of the key requirements for such a behavior is that you need some very dense spectrum of states. So for black holes, you know, we expect we have a finite entropy. That's certainly what the CFT gives us. I guess there are still corners of the relativity community that think black holes have infinite entropy, and you have a whole asymptotic region on the other side of the horizon or something. I'm not going to be taking that point of view, so I'm just going to assume we have a single conformal field theory. We know we have a discrete spectrum of states for any given energy. We have a finite number of states below that energy. And I'll assume that the kind of CFTs we will encounter will have this dense spectrum of states in this Hilbert subspace that we're describing. Okay, and another feature that we'll assume, it's maybe not too critical, but it will be helpful in making some estimates, is that we'll assume these black holes are acting as fast scramblers. So what this idea of a scrambling time is essentially a kind of global thermalization time. So your worst case scenario, if you like, for trying to estimate how long it's going to take for some perturbation or change in the state to scramble. Susskind and Sakino have suggested that black holes are fast scramblers. So what typically happens is, instead of a log of the system size, you would get some, characteristic length. So in this case, just the horizon size, but it would be multiplied by some power of the system size rather than a log. So that's typically what you would find, for example, in some kind of gas of molecules or something. The scrambling time would go like some power of the system size. Here we're going to be assuming that the scrambling takes place much more quickly. That, as Preskill and Hayden showed, if that is true, then black holes actually will emit quantum information within this time. So yeah, once one is in this regime, the horizon in some sense behaves a little bit like a mirror. So if you actually had access to the state of the radiation outside the black hole, once more than half the radiation has come out, you can start reconstructing the quantum state of things that you send in with high fidelity. Okay, so we've got that fast scrambling criteria, and yeah, we're just assuming, as I said before, that the number of states of the black hole is finite and the exponential of the entropy, and I will be frequently dropping factors of order 1 when I write these kinds of equations in a somewhat random way, fortunately. Okay, so that's the basic setup, and we're going to apply this eigenstate thermalization hypothesis to this Hilbert subspace. So the eigenstate thermalization hypothesis is very easy to state. It comes out of a lot of hard work going back to the early 70s by Michael Berry, and has had various revivals over the years. Mark Srednicki was working on this when I was a postdoc in Santa Barbara in the 90s. And that was one of the key revivals that has been very successful in bringing it to a wider audience. And the way he said it was very simple and straightforward. So you imagine you're working on this big Hilbert subspace. So these states labeled by alpha and beta are going to range over this subspace of work with a size e to the entropy of the black hole. And we're going to work with energy eigenstates. Okay, so we then just pick some set of observables, and you're not allowed to pick too many observables. You know, if you pick too many, you can kind of do a change of basis to kind of make this hypothesis false. So we're going to have some finite set of observables with a number much, much less than the size of the Hilbert space. And the statement is pretty straightforward then. So in this energy eigenstate basis, when we start looking at matrix elements, we get a diagonal term. And this is some smooth function of the energy. And we're, again, so there are other restrictions on these observables, like they have a nice classical limit. So I don't know, something like, say, the position of a particle, or the curvature at some point in space-time, for example. So we don't want kind of explicit factors of h bar in the definition of our observables that would, so that as we send h bar to 0, we wouldn't have a good classical limit for the observable. Okay, so these A's are going to, you know, typically have some contribution even when we send h bar to 0. And then we get this off-diagonal term. And you can compute this dependence here on the entropy of, so S is the entropy of the black hole, or the entropy of this Hilbert subspace at some given energy. And this R is just some random matrix, which is often assumed to be some random Gaussian. That's one of the things you'd really want to compute using some more complete theory of quantum chaos. But yeah, this is a tremendously liberating formula, because it tells you that you know, you don't really need to worry too much about extracting all these very difficult things from your conformal field theory, because at the end of the day, they're just kind of random. And as we'll see, they will drop out of any kind of semi-classical limit. On the other hand, these are the terms that are unitarizing the whole scattering process, or the formation and evaporation process in the black holes. So they're crucial for seeing how unitarity emerges. Okay, so that's our basic setup. And again, it just works within this Hilbert subspace where we think we have quantum chaos happening. You know, if we had an integrable system, this R, instead of being some completely random matrix, would have much more structure to it. Okay. Okay, so we've got a hypothesis for all these matrix elements once we can go to this energy eigenstate basis. But there's, I guess, a little bit of a fly in the ointment now, because our small black holes are very far from energy eigenstates. And let's, I guess we could go back to our picture coming from Mukhanov and see that, you know, this is clearly some kind of non-stationary process. So if we want to take this and make a stationary process, well, it's kind of good we have ADS there, because that will kind of turn this radiation around as it reaches the boundary of ADS and generate something like this coming back in. And then we can take some superposition of such states where we, shift in the time direction to get a stationary state. But at the end of the day, we have something that's extremely non-classical. Usually when we talk about black hole states with some fixed energy, we have in mind a very specific space-time geometry. And what we're saying now is we have, for small black holes, the energy eigenstates are completely non-classical. So they're a superposition of stuff coming in, stuff coming out, and black holes sitting there, all kind of mushed together in the time direction. So there's no classical geometry associated with that. We're really taking a quantum superposition of all such geometries, which of course we can easily do in the holographic description. But these energy eigenstates don't seem to be even accessible from the geometric point of view. Okay, so we have then these superpositions of black holes and clouds of ingoing and outgoing radiation. And we're in a very different regime from large black holes in ADS, where all we have to do is put things at finite temperature and then use Euclidean time methods to do things like calculate the entropy. Of course, in a CFT, that's easy to do if you're not worried about numerical factors. If you have a conformal field theory, then what the once you introduce a temperature, what the entropy is going to be from dimensional analysis. So that all works for large black holes, and you seem to get some nice geometric saddle in the imaginary time formulation. For small black holes, it seems like all that is out the window. And I should maybe comment that originally our motivation was to try to make some kind of connection with these island formulas. That didn't really seem to emerge terribly readily at this point. But yeah, maybe in the future one will be able to see those time-dependent saddle points a little more clearly. But it's tough just applying Euclidean methods to these extremely time-dependent superpositions of states. So that's what our energy eigenstates are. But if we want to build something that actually looks semi-classical, we then need to build some kind of superposition of such energy eigenstates with some fixed width. And here we'll do a kind of variation on the calculation that Mark Srednicki did in his paper, where instead of looking at long time averaging, we will focus instead on averaging over states, typical states at some fixed time. So it'll be a somewhat different averaging procedure. But the idea is somewhat similar in the sense that if we're going to use these ideas of quantum chaos and make contact with some semi-classical limit, we want to build some state that's some superposition of energy eigenstates with some width. So I'll define that to be the width. And typically this width will be inversely related to the lifetime of the black hole. So it might be 1/n cubed. That's a pretty narrow width. if you were to just take a bunch of particles with temperatures of order 1/m, the typical width would actually end up being of order the Planck length, or order 1 in these units. So yeah, this is already pretty narrow. We could certainly make states with wider widths that would obey the kind of bounds we're going to show even more tightly. Okay, so once we have these widths, it opens the door to having self-averaging. And given we have this extremely dense density of states, we expect our level spacing to be of order e to the minus s, or e to the minus m squared. Okay, so with that setup, we can try and do a calculation of a fluctuation in one of our appropriately chosen local observables, not too many. So defined at some particular time, say, we don't want to include non-local observables where we're having to pick out a frequency by, say, integrating over time. So something that's local and not too numerous. And we'll just make a condition when we compare these two different typical states that they have the same energy, just for convenience. And we'll allow their widths to be similar to each other up to some constant. So C is just going to be some constant here, not related to the central charge. So then we just apply this eigenstate thermalization hypothesis and compute this. And we'll get two kind of contributions, one from the diagonal piece, one from these off-diagonal pieces. So the diagonal piece is really the piece that you would expect to match perturbative gravity effects, which will obey this criteria that as we send h bar to 0, they have some, they're still present. And these off-diagonal pieces that will typically fall off exponentially fast as we send h bar to 0. Okay, so the diagonal piece is pretty easy to compute. And it ends up being proportional to the square of this width, and involves the, I guess that should be a curly A there, the second derivative of that function that appears on those diagonal elements. As we said, that's a smooth function of energy, since as h bar goes to 0, it's just coming from some kind of classical gravity terms or some leading order CFT terms. So this is the part that you would expect to kind of match against some semi-classical approximation. Okay, so in particular, our conclusion from this is that this piece doesn't depend on the black hole microstate in any kind of very sensitive way. It just depends on the expectation value of this average energy. And that doesn't change very much as we go from one microstate to the other, within, assuming this width is reasonably small. Okay, so the more interesting pieces are these off-diagonal pieces that unitarize the evaporation process. Okay, so as we said, they're multiplied by this random piece. And in quantum chaos, people aren't usually too fussy about exactly specifying what R alpha beta is. I guess one could get to the point where you try and specify it more precisely, and maybe that's an interesting thing to look at in the future. But following the kind of assumptions that Barry and Srednicki make, we'll just assume that the entries are just Gaussian with, say, a width of unity. And one way to make these off-diagonal contributions big is then just to pick an eigenstate of R. And the way we're setting up the calculation, we're free to pick our state to be whatever we want. We could pick an eigenstate of R. And if we do that, we get an enormous, a contribution of order 1. Okay. So we can see contributions that will completely blow the classical contribution out of the water if we adjust our state to match the randomness in R. Okay, but then you have to ask, well, what's the likelihood of picking such a state? And if you were to just pick it from some unitary ensemble, so you've got a vector space with a size of order e to the m squared. If you want to make each entry close to some eigenstate of R, you end up having to adjust it to within some small parameter epsilon to the power of e to the m squared. So it's a double exponential in the size of the system, so it's extremely difficult to pick such a state. They are there, they look very non-classical if you manage to hit upon one, but they're extremely unlikely. And one always has this kind of issue with these kind of quantum chaos calculations, and you make some argument that such states are not statistically dominant. So you can instead just pick some typical state, and the width, there's very little restriction on the widths. You could even make it much smaller than the inverse lifetime. And for any such set of states that are that give you some kind of reasonable self-averaging within that width, you will get an exponentially small contribution from these off-diagonal pieces of order e to the minus the entropy over 2. Okay, so you get quantitative estimates of how these unitary effects are going to show up in any local observable that you care to compute. So you are able to quantify this microstate dependent contribution to the observable, and it's exponentially small for any reasonable choice of state. Okay, so that's, I think, a nice way to better quantify the kind of effects we expect to see that are arising from holography and acting to unitarize the evaporation process of the black hole. So they don't have to be very big. That's how big they have to be. Okay. So it's possible to, instead of looking at these local observables, look at something like transition amplitudes. And when you're looking at a transition amplitude, you're free to do any kind of projection onto an outgoing state that you want. So in the language we were using before, that would be some kind of non-local observable. And as we've seen from this eigenstate thermalization hypothesis, we get some non-vanishing amplitude to go to any other semiclassical state. It's exponentially small, but it's non-zero. So what does this mean? Well, you're kind of saying, well, you could say send in some null shock wave and make a black hole, and then some other energy profile will emerge at some later time. It could be any kind of semi-classical state you want with the right amount of energy. And we're saying that there's a non-zero amplitude to go between those. Okay, and it even tells us what the answer is. It's of order e to the minus s over 2. So this gives us a way then to estimate how badly the semiclassical approximation is doing near the horizon of the black hole for this kind of transition amplitude. Okay, so we said before for local observables that there's almost no effect. We get a lot of self-averaging over different outgoing states. So semi-classically, it looks like everything's doing well. We start looking at these transition amplitudes, kind of the opposite happens. And if we wanted, we could evolve this back semi-classically and see that near the horizon, we get extremely large corrections that are as big as the classical effects near the horizon. So a byproduct of holography then is that we're going to, for these small black holes, we're going to get extremely large quantum effects near the horizon when we compute transition amplitudes. So the claim is all these large corrections average over each other and disappear when we compute local quantities. If we were trying to explain some kind of matrix element that one might extract from this kind of process, we're going to see GR break down dramatically outside the horizon in order to explain the e to the minus s over 2 transition amplitude. Of course, you might have said, well, you know, we have completely different saddle points and the Euclidean sum over geometries, but yeah, that doesn't always mean very much when you're computing these kind of genuine time-dependent processes. And I guess, yeah, my inclination would just be to say the holographic description is giving us a way to compute these things, but we don't really have a very geometric way to think about that near horizon geometry for this kind of transition amplitude. And the holographic theory is giving us the bridge that allows us to make sense of that in a detailed way. Okay, so yeah, as I said, you do need some kind of non-local operation to do this projection onto your outgoing state. So it's not a contradiction with what we were saying before. Okay, so anyway, so the upshot is if you were to do a semi-classical calculation here, you would find that it broke down well outside the horizon, where these kind of two states start to overlap each other. Okay, so otherwise, if we are just computing local observables, we'll get this self-averaging, and these kinds of effects will not be present. So conversely, these local observables are not enough to project us onto an outgoing state. Okay, a little bit of time left. So let me just say a few words about infilling observables. So a lot of it relies on this paper from 2015 I wrote also with Laurus. So we're going to, I'll spend a little time reviewing that. And we're going to assume that we began with some kind of semi-classical state to form the black hole, and then try and use the arguments that we used with the eigenstate thermalization hypothesis to be able to compute these observables. And this earlier work kind of explains why the definition of these observables is insensitive to perturbations that act earlier than this scrambling time. So let me take a few moments to describe that. Okay, so we're going to kind of try to package our infilling observables in terms of some bulk effective field theory that we'll then try to compute using holographic methods. Okay, so we're just kind of using this effective field theory as a way to package together our full set of bulk observables. And we're going to use some ideas that Ted Jacobson and others used in the early 90s. So they set up a similar kind of lattice effective field theory, and their goal was to explain why Hawking radiation coming out was kind of insensitive to the lattice structure, which is something that seemed to be emerging from these kind of condensed matter analogs of black holes that you can get with fluids going down plug holes and that kind of thing. So we're just going to take a spatial lattice and choose these lattice points to move along time-like geodesics. So I guess T will be the ordinary short shield time, but Y will be a spatial coordinate that's adjusted so that these move along straight lines. So this infilling coordinate system will propagate toward the singularity, which sits on this line. Good. Okay, so that's our setup. This is the same thing with some more details. Here we're mostly just thinking of this effective field theory in the vicinity of the horizon, and it is true that these Y coordinates have some issues as you go out to radial infinity, but we're not going to worry too much about that. So to kind of pull out the physics from this, we want to essentially just solve the wave equation for a massless field on this lattice. And Ted Jacobson, noted that for Hawking radiation coming out in this region, you get the predicted Hawking spectrum as you get rid of the lattice. We'll not dwell too much on that. So what Laris and I instead focused on was what was happening inside the horizon. So if inside the horizon, if you send a light ray off, it will hit the singularity. So this is a light ray moving off to the left and hitting the singularity. And here's a light ray moving off to the right. And again, that will also hit the singularity. But the regulator now gives these light rays a time-like group velocity. So even if you try and send your light ray off from the first point inside the horizon, it will always hit the singularity. We computed the time that it takes to hit the singularity, and it's of order the scrambling time that we showed before, n log m. So this gives us a way then to begin building holographic observables, because what it's telling us is that this usual problem where you have a continuum of soft near horizon modes is regulated. So again, if we have a black hole that we're actually forming in a single CFT, we don't see any sign of these kind of weird shocks that can run along the inside of the horizon, which some people thought would give us firewalls. It's just completely regulated in the effective field theory. And of course, this is the kind of thing that matches numerical simulations of black holes. If you talk to a numerical relativist, they would think you're crazy if you started talking about firewalls, because they do numerical simulations of general relativity on such lattices and see perfectly smooth behavior as you cross an apparent horizon for exactly this kind of reason. So we regulate this continuum of near horizon modes, which otherwise would, we would have finite wavelength, arbitrarily small frequency modes, otherwise that could potentially contain an infinite amount of entropy. And that's a problem that goes back to Tufts brick wall calculations of the black hole entropy, where he tries to account for the entire horizon entropy using such modes, but they kind of completely disappear when we regulate it in this way. And it gives us a way to set up infilling observables. And since I'm almost out of time, I'll be a little bit brief here, but the idea is really just that we take some patch of space outside the black hole, and let's say we specify that nothing fell in a scrambling time before that, and that gives us some set of observables that, again, we can use the HKLL construction to build, especially if they're far enough away from the black hole. And one of the observables that we can build is, of course, the infilling Hamiltonian. So we can then start evolving those states across the horizon, and we get a kind of self-consistent effective field theory that we can view as being completely calculated in a holographic way and push those observables across the horizon and compute expectation values. And as long as we don't have too many such observables, and if you, there's some estimates in the paper where we show you don't get too many observables, then you can use those ETH arguments, as I made before, to just argue that these exponentially small corrections are in practice unobservable. And it's really just this diagonal piece that's coming from the classical part that is going to affect those observables. Okay, and of course that picture ends when those observables hit the singularity, and then all bets are off. Okay, so just let me make the conclusions now. So one of the surprises for me, I guess, were that these energy eigenstates for small black holes are completely delocalized. And thinking back, I really can't imagine having done this calculation in asymptotically flat space, because you don't get this effect that the boundary of ADS will really give you something like energy eigenstates. You can get the states to scatter back, and you can build things that are stationary in time in ADS. It would have been hard to get this kind of picture to hang together at all if you were in asymptotically flat space. But nevertheless, the picture gives us a nice way of seeing how this classical evaporation process emerges for small black holes in ADS. Okay, so we have these energy eigenstates that are highly non-classical. To get quantum states with good classical limits, we have to superpose in some band of energy eigenstates. And then we get self-averaging over many states. Of course, since our assumption was that evolution is unitary, that's not really the interesting question here. The interesting question, as it is for any chaotic system, is how you get a semiclassical limit emerging. And the whole point of the eigenstate thermalization hypothesis was to provide some explanation of that. So it seems like we can apply those ideas here and see how this semi-classical limit emerges for small black holes in ADS. So maybe I'll end there and see if there are any questions. Thank you.
Thank you, David, for this very interesting talk. And let's open the floor for questions.
So yeah, thanks for your nice talk. I didn't get what you wanted to tell us about these firewall states. So you claim that you can really build those firewall states, kind of, or?
Yeah. So once you have this R matrix, so R is just some set of entries that are Gaussian with random Gaussian entries with width of order 1. I guess the width being of order 1 is important for getting this e to the minus s prefactor that you can pull out. So yeah, if you were to pick, let's say just this state, so yeah, let's say we just wanted to compute this matrix element, and we made psi an eigenstate of this R matrix. Okay, so yeah, well, I guess if I'm putting these energy factors in, I want to make it an eigenstate of that whole thing. So you can compute this off-diagonal piece for such an eigenstate, and the off-diagonal piece gives you an answer of order 1. Okay, so what would have self-averaged for a typical state instead adds up, and it can be as big as the classical piece. So there are states there that behave highly non-classically, even for these very local observables. So if you could build such a state, well, it probably wouldn't, it would look much worse in some sense than a firewall, because the fire would extend quite far outside the black hole. It would look like perhaps a star or something. But it would satisfy all these criteria that, well, yeah, so we could perhaps build such a state and think of it as coming from some very special cloud of gas, but then it would, instead of forming a black hole, it would form something more like a star in the center here, rather than something with a smooth horizon. But yeah, it's extremely difficult to tune things to get that to happen.
Yeah, but it's not a kind of a firewall state in the context of like AMPS, in the sense that you break up the entanglement, or that you basically give an explanation why this entanglement is broken up between early and late Hawking radiation in the interior of the black hole, or?
Yeah,
it's an object.
Yeah, you wouldn't, in some sense, be able to probe the interior because the geometry would break down so much already outside the black hole. So yeah, it's not a very clean firewall in a sense.
Okay, thanks.
Okay.
Other questions? I have a question regarding your exactly this slide actually. When you write energy eigenstates remain energy eigenstates, can you say how exactly you mean that in a time-dependent system that has a Hamiltonian that depends on time?
Well, so usually the Hamiltonian doesn't have any explicit time dependence.
What do you mean by usually? I mean, there's systems that like we write down holographically where the action is time dependent, and you would also have a no time translation invariance, which I would express field theoretically in terms of a Hamiltonian, which is time dependent.
Yeah, so here I imagine we're just starting with some ordinary conformal field theory that is, has some gap in its spectrum and is reasonably dual to Einstein gravity and some large n limit, with a negative cosmological constant. So I'm not adding in any extra sources. So when you compute the, say, L0 for that, well, if you were to compute L0 in terms of, if you had, say, a field theory dual for your conformal field theory, there wouldn't be any explicit time dependence. So you can, yes, there are many interesting things to do where you put in time-dependent sources. But I'm not really, yeah, when I talk about the Hamiltonian, I'm not including those kinds of terms. So yeah, I imagine I just have a time-independent Hamiltonian, and then I have stationary states that are all changing phase with e to the minus I et. And yeah, if you just have such an energy eigenstate, there's no quantum chaos. It just rotates.
Okay, yeah, thanks. I understand now. So you're considering the whole system, not a subsystem which is in contact with some environment. Like, which is what one would need in order to have a time-dependent Hamiltonian.
That's right. Yeah, I'm just doing things in a very I'm trying to.
Okay, so I was just confused by the general statement here. So I misunderstood the statement for like stating a general truth as opposed to restricting the scope of what you're thinking about.
Yeah, so the CFT itself is not changing, but the magic is kind of happening when I make this restriction to the Hilbert space of the CFT by focusing on this particular set of states that are directed inward radially.
I mean, the idea of decoherence is the same, right? So you like the idea of just quantum decoherence when you consider a system that is in contact with some environment, then your subsystem will slowly decohere because it gets entangled with the environment more and more, and somehow it seems like at least similar in what you're actually able to calculate here.
Yeah, I've kind of taken a slightly, I made things a little more simple because I've imagined taking a particular time slice where we have something that just looks like that, say. So that's a superposition of energy eigenstates, but there's nothing else in the game. And certainly, yeah, if you had extra radiation in addition to your kind of what comes out of a single black hole, then it would all kind of mix together, and when it bounces off the boundary of ADS, You might question how often you actually get a black hole in the middle, and yeah, I mean, I think it's possible to kind of extend these considerations to things like, rather than talking about states, talking about density matrices, for example, which would then obey some kind of equations where you're coupling to some outside environment. But yeah, I've simplified things a little bit by getting rid of that outside environment and just having kind of the product of a single black hole in the game.
Well, I like that approach because you can always view your whole system as partitioned into a subsystem and environment, and then you can like write down expressions for your Hamiltonian in the subsystem, and then you know exactly what happens when you exchange energy or entropy with the environment, right? So I mean, that's how I would see the strength of what you have done.
Okay. Good.
So I mean, I'm just trying to understand. So this is very interesting. Thank you.
Oh, thanks.
So are there any more questions? If not, then we should thank David again. Thank you so much.
Oh, thank you.
Thank you.
It was fun.